Okay, so we have domain restrictions with radicals, square roots, fourth roots, even roots. We have domain restrictions with rationals, which are fractions, and we watch the denominator. And we also have some domain restrictions in context. And what that means is if a function has real-world context, it may add additional restrictions on the input values. So for one example, let's find the domain of a function that determines the average weight of a person depending on the person's height. Okay, so the input is going to be height, and out comes the average weight. All right, so suppose you were 5 feet is the input. So f of 5 feet would be how much you would weigh for a 5-foot average person. It doesn't say male, female, or anything like that, age. It just says average. So this is a pretty weak example as far as reality, but let's just say we'll put 110. I have no idea. I'm just making this up. Okay. So, but the point of this example, what I liked about it was, can we put in 10 feet? Is 10 feet a good example of our domain? Well, I can't remember what Ripley's Believe It or Not or the world record, Guinness Book of World Record is for the tallest person, but do you see how we have domain restrictions here? Are we going to put in f of 100 feet? I can guarantee you that's not going to happen on this planet. And what about f of negative 20 feet? Okay, so do you see how these the ones that I'm giving you right now, this guy and this guy and this guy, those really, I don't know about the 10 feet. That might be the record or something like that. I'm not sure. But we would have to research to get the appropriate domain. For sure, we don't want any negatives. We don't want any negatives. What about fractions and decimals? Is it okay to say I'm 5.5? 5 feet 3.5 inches? Yeah, 3 3/4. Okay, so you want to think about fractions, decimals, whether it's just integers, negative numbers. These are all the things we need to think about when we restrict a domain. Okay, so let's go to one a little more specific here, which is actually a good problem. Okay, so this is a change machine. You can put in an X dollar bill. That means whatever X is, whatever we have for our dollar bills, it's going to give you f of X nickels in return, equal in value to X dollars. Any current legal denomination of US paper money can be fed into the change machine. So what would the domain of our function be? Okay, so we can put in an X dollar bill and it's going to give me f of X nickels. So let's just try a few. Okay, can I put in X equal to 1? Can I put in a $1 bill? So that means that f of 1 would give me how many nickels in a dollar? There's 20. I'm just going to write 20 nickels. So that's cool. Can we put in a $2 bill? Yes, we can. We'll get 40 nickels out of that. It says any let's see, any current legal denomination of US paper money. So what is our domain going to be? Can we use interval notation? No, we can't, because we don't have fractions and decimals, $1.50 bills, $2 3/4 bills. We need to list specific in this. This is why we have set notation. So we have a $1 bill, we have a $2 bill, 3, 4, no, 5, 6, 7, 8, of course not, $10 bill, $20 bill. I believe there's a $50 bill, and I believe there's a $100 bill. Now, what is going to be a reasonable domain for this change machine? It says you can fit any in there, but if I put in $100, f of 100, every dollar has 20 nickels. That's going to be 20 times 100, or 2,000 nickels. Is that going to work? Well, that depends on where I'm at. Okay, if I'm in Las Vegas, maybe. If I'm in my local store, I don't think so. So we have to think about what's a reasonable domain for the actual real life situation that we're talking about. Okay, so I'm going to throw that 100 out because I don't believe that's actually very reasonable. Okay, and let's just close that with 50. I don't even think a $50 bill is, but you know, it's 50 times 20 would be 1,000. Yeah. Okay, so there again, can you see how it just depends on the situation? So let's go to another situation. Actually, this will be our last one in the video. All right, we've got a car. It's using gas at a constant rate. Okay, so after driving 25 miles since a full tank, there were 9 gallons left. After driving 65 miles since a full tank, there were 7 gallons left. We want to use a function to model the amount of gas in the tank. Let the independent variable, that's my input, so the independent variable is x, be the number of miles. So we're going to let x equal miles driven. Miles driven since full. And then the function is going to model the amount of gas in the tank. So f of x will be the amount of, actually, I'm just going to put gallons because it's in gallons right there. Okay, so the gallons of gas. Okay, in tank. Okay, so what have they given us? After 25 miles, 9 gallons. So x is miles, so 25, 9 gallons. And 7 gallons, full, there it is, 65 is my miles. I want that for my x, and 7. So a constant rate, that means I can use a linear function. All right, so now I have this data, and the easiest linear function we have is slope-intercept. We have 2 points, so let's find the slope. Will be the y, difference in y's over the difference in x's. So I'm going to take 9 minus 7 over 25 minus 65. So I'm going to get 2 over negative 40, or negative 1 over 20. Okay, so that could be a decimal because I know that's 0.05. So it's up to you. If it comes out to an exact decimal, you can use it. All right, now I'm going to pick one of those points to use. I think I'll use the 9 for y. And there's my slope is negative 1 over 20. And my x is going to be 25 over 1. Okay, I need to simplify this and solve for b. So let's see, I'm going to simplify this. 5 goes in there, 5 goes in there, and I get 9 equals negative 5/4 plus b. So if I add 5/4 to both sides, I will get b. So 5/4 is, let's see, 9. I'm going to do this little addition. 9 over 1 plus 5/4. Well, if I times these both by 4, I'll get 36/4 plus 5/4, and I'm going to just keep it as b equals 41/4. Okay, so my function is going to be, that's my y equals, what's my slope? Negative 1 over 20 x plus 41 over 4. All right, so that was the first thing I think they asked us to do. Let's go back up here. Find this function's domain and range. Oh, I did all that work for, well, there's the function. There's a little review for you on how to find a linear function. Now, what would the domain and range be? Let's think about this. The domain is how many miles driven since full. Okay. The range is going to be the gallons of gas in the tank. So what do we need to know to decide what the domain is? Well, how far can my car drive on a tank of gas is pretty much going to be the domain. Now, in this case, I'm going to use interval notation because because I can use fractions, and you've seen the machine when you buy gas, it's 3.5 gallons or something like that. So it's going to go from 0 to, let's see, my car is about 11, 12. It depends on the car, depends on how many gallons in the tank, right? So let's say it's a 15-gallon tank. That's what I'm going to say. Oh, sorry, I'm doing the range, aren't I? That's the gallons in the tank. Okay, let me go back here. Sorry to confuse. So I'm going about how many miles can I go if there's about 15 gallons in the tank? Okay, so I went 65 miles on 7 gallons. Maybe this doesn't get very good mileage per gallon. It's getting about 40 miles per 2 gallons, right? So it's getting right here's our rate, 20 miles per gallon. Okay, so let's say I had 15. I'm going to just use my a 15-gallon car. 15 gallons. That's going to be 15 gallons, 20 miles per gallon. That's going to be about 300. So I could drive from 0 to 300 miles. And my range is going to be how many gallons are in the tank. So the range is going to be from, let's see, the highest would be 15. So it could be from 0 to 15. And this is gallons, and this is miles. So, okay, so you got a little bit more for your buck there. All they really wanted was the domain and range. Okay, so now I believe you're ready to go ahead and do the practice problems. Okay.